those in the tropics, those in the temperate zone. And then for each of those, there's 0 to 10 tons per hectare, 10 to 40 tons per hectare, and 40 plus. So what you see is in the 0 to 10 range, it's positive in all of the groups. What you also see is that, especially in Model 1, it drops off pretty rapidly. And see, when it drops off, we're not saying it's going to make plant response go down. What we're saying is that we're going to have less and less positive benefit. A couple things to take away from this. Where I modeled yield response together with biochar highest treatment temperature and together with soil pH, see an initially higher response than the equivalent grid doesn't model it, and also a faster decline. So what that's saying is that, well, what I'm trying to infer from this, what I think you might be able to infer from this, is that there is a quick response from something having to do with the pH of the temperature, that then it's done at lower temperatures, and more biochar won't do any more good. That's sort of what I think I can pull from the difference between that and that. It's hard to make much conclusion about the tropics because I don't have enough data to estimate the model for the subset in Model 1. It's hard to pull any conclusions from the non-fertilized. And interestingly, with the temperate, it's really similar looking, a little different. But what that suggests, I don't know if I can say this causally yet, but what that suggests is that maybe high treatment temperature and pH are less important in the temperate zone than somewhere else. So that's that one. That's the main results from the study. Here's some regression coefficients. Essentially, these numbers here are pretty much those betas from the models here. And so essentially, what this is saying is that so pretty much anywhere where, for those of you who haven't looked at regression in a while, anywhere where these error bars don't cross the axis, that's going to be statistically significant, and you're going to get a number of stars indicating statistical significance next to the value. The interesting thing about this slide is that highest treatment temperature, pyrolysis temperature, is significant in a lot of the subsets, and in all of the subsets at the lowest application range. So temperature plays a really big role, and in all cases, it's a positive value. In all cases, it's a positive role. pH of the soil, same thing, but negative. So the higher your soil pH, the less plant response you're predicted to get from these models. And in many cases, it's significant. Sometimes it's not, but in most it is. One thing to emphasize about these models is that the way this is parameterized, I didn't mention anything about this little guy here. So obviously, a lot of things go into plant response to biochar other than the temperature of the char and the pH of the soil and whether or not it was fertilized. All that stuff that I don't observe goes into that error term, and we don't know what that error term is. So that's the caveat on all these sort of analyses and all these sort of models, is that this is the best estimate we can do with just these data that we have. If we had other data points, maybe they'd go up and down, we don't know, but this is what we can do at the moment. So yield, any questions so far? Yeah.
Is there any data on if there's irrigation, if it's rain-fed? Or
No, that's a major gap in literature. So for these studies, all the greenhouse studies had water controlled. All of the plant trials, all of them experienced the same. None had water different from the other. That wasn't a confounding factor in any case. But these data you can't pull apart the influence of water.
All of the efficacy of biochar in different soils, sand, clay, or soil.
So one thing I'd really like to do is look at it across soil orders. So mollisols versus alphasols versus ultisols versus octasols, etc. There's not enough data. Not enough data. Very few studies actually report. Very few studies report texture. In part because it's a huge pain to do in the lab, but yeah, it's commonly not reported. So, okay, yield response at highest treatment temperature. These three equations here are for all paired growth trials, the tropical and the temperate. So this is yield response per ton per hectare of biochar is equal to this coefficient, model coefficient, times the highest treatment temperature, whether or not it's fertilized, and the soil pH. In general, every time you go up 1 degree of temperature, you increase your yield response per ton per hectare by this small number. Highly significant. But what to take away from this is that in the tropics, this number is a lot bigger than this number, and this number is a lot smaller than this number. So in tropical soils, statistically speaking, we can say that soil pH, working together with high treatment temperature, is a major predictor of plant response. In the temperate zone, you have the same relationship, but it's a lot bigger, and this is not significant statistically. So that's that. So this one here, these charts are a measure of biochar improving soil relative to a baseline. These units here, this is delta change in pH divided by the initial soil pH. So say you started with a pH of 5 and you increased it to 10. You'd have, that term would be 2, for example. So if you have a very low initial soil pH, it makes it much easier to be the high end of this. If you have very high change in pH, it's the high end of this. But it's going to be sort of a non-linear thing with diffraction. So essentially what this is saying is that as this term should be thought of as the improvement in acidity. As the improvement in acidity increases, plant response is very well predicted by that. But it's better predicted, this delta pH over initial pH term is much more predictive in the tropical zone than in the temperate, although it's significant in both. And it works across the whole group also. This is the same thing. Delta is the change in cation change capacity divided by initial cation change capacity. It's logarithmic. Same thing, it just goes like this instead of like that. The relationship's weaker. Oh, this should say temperate. It's the cation change capacity relationship. The improvement in pore cation change capacity is a much better predictor of plant response in the temperate zone, but it's not significant in the tropics.
Is that backwards? Is it?
Yeah, this should say temperate.
It definitely should say temperate.
Yeah, that should say temperate.
When you get an increase in cation exchange capacity
From a low value.
From a low value in temperate soils.
That's predictive of yield response.
Better prediction of yield response in temperate zones. In the tropics,
the
improvements in cation exchange, but tropical soils would have lower cation exchange capacity to begin with, wouldn't they?
This is what the data is telling me. I mean, You're right. Everybody sees this as surprised. It could be that we just need more data. It could be that this is really a thing. So that's the data. I'm going to go on the implications from here. Any more questions on the data or how I estimated this kind of stuff? Or yeah.
I was curious if there was any sort of control on how deep the biomass
Good question, and no. Most of the greenhouse studies, you can be fairly confident. They often say that they mixed it throughout the pot and it's well homogenized. In the field trials, often they spread it over the surface and they disked it in. It varies, so I don't control for that. That would show up in that epsilon term.
What are the ranges around your treatment temperatures?
Sorry?
What are the highest treatment temperatures you work with?
It goes from 310 to 600. 310 to 700. Yeah. Others? So, obviously I'd love to do an analysis, talk about how much available phosphorus is in the biochar, how much water holding capacity it has, nitrogen, blah, 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 blah. Based on what I have, I'm going to go into some implications I think that can be drawn from this study.
I'm sorry, I answered the question.
Please.
Is there any control, or how do you know what they need to feedstock?
Yeah, so feedstock, that's another huge blind spot. I mean, one of the problems with feedstock is that it's clearly a critical factor in the biochar itself, but you can't really put that into a number form very easily, can you? Maybe, one thing I might try to do would be to have a dummy variable. So is it a woody feedstock? Yes, no, and see if that's significant. Is it an animal waste feedstock? Yes, no, is that significant? And theoretically it should show up in the chemical properties of it, which are heterogeneously reported. So it's commonly, like, for example, a lot of studies for no particular reason, one of the most common temperatures that the stuff is produced at is 550 for these studies. And so a 550 char made from municipal green waste in Australia is going to have a pH of like 8.5, and a 550 char from poultry manure is going to be highly alkaline to the point of burning you and be 13. So a lot of the stuff would show up in the chemical properties. Some of them might not, but I think actually I might try to parameterize it in terms of categorical variables for the future. But yeah, feedstock is not able to control.
Nice to know the nutritional value for an active biochar.
Oh, sure. But commonly wood has nutritional value in it. It's just got so much carbon bound up in lignin and stuff that you wouldn't add it to your soil because you mess up the carbon-nitrogen ratio. So some things, biochar turns some things that wouldn't be nutritional and makes them nutritional by making the carbon something that a microbe couldn't eat.
Are you using corn, like what's the crop that you can grow in these days?
So a bunch, and I'm generalizing across crops, which in the future when there's more data you probably wouldn't want to do. But right now this is what we have to do given the paucity of data. Rice, corn, radish, soybean. That's pretty much it. And and this is gonna throw in some bias because corn really needs nitrogen, and that's going to, and biochar doesn't supply nitrogen, but it improves nitrogen sort of recycling in soil. There's evidence for that. Soybean is the opposite; it makes its own nitrogen, so it's going to have different responses to this kind of thing. Others, so it's the different crops is definitely a weakness in the study. Others? So, implications. So, biofuel may be a byproduct of biochar, not vice versa. There's one good economic modeling study looking at the economic value of biochar. It's based on corn in the U.S. Midwest. If I plug in my values for yield response into his model, I get beyond the break-even point, where he wasn't quite at the break-even point, and I get that the value of the char is more valuable than the energy value that's produced as a byproduct of the char. It also would argue in favor of the char producing and less biofuel producing slower pyrolysis rather than the fast one. So that's one implication. Of course, more data would be nice and more models would be nice. But this idea. I think this study can maybe provide a data point for people to, when people need a value for yield response to biochar, they can use this one as the best current estimate. And using that one with this one particular model, it appears that the value of the char is higher than the value of the energy. Soil saturation with biochar. And by saturation, what I mean, the point where adding more doesn't give you any more benefit, is unlikely to be a limiting factor for mitigation. The optimal values of the asymptotes are high. You can keep on adding more and you'll still get a benefit for quite a long time. Biochar is preferentially transported. If you add stuff to your soil, it will wash away, it'll get blown away, or it'll trickle down into the soil. That's been observed in a lot of studies. So it's, it's not like you lose your investment entirely, but it's over the long term you'll need to keep on adding more because it'll go away. It is low density. It's hard to add a whole lot at once.
Well, a good point to make also is that you're not losing the carbon sequestration value at all.
Right. So that's a good thing from the perspective of sequestering carbon.
Even if it ends up in water.
From my perspective, it's great. If you're a farmer, maybe you want to stay there. I don't know. But yeah, absolutely. Thank you.
Unless farmers actually get paid to sequester carbon, in which case they're going to be asking more the question, well, can I add more without affecting the increased yield I've already gotten from the first application? Your suggestion is that is not likely to be a problem, which means that the funded sequestration becomes very attractive to a farmer because he can continue to apply it and not worry about this stuff, not worry about compromising his yield.
Exactly. There's no evidence that if you add a whole lot to your soil, there's no evidence that'll do anything bad. There's a point to which it'll stop doing any more good, but there's no evidence that'll do anything bad.